value. And can 3D keep pace with 2D? These 2D standards, there are 2D standards that are moving very fast right now. 3D needs to keep up with that. We're really a 3D cinema company in a lot of ways, and so we want to ask the question, can we keep up? At RealD, we really view the stereoscopic cinema as a system, and we try to optimize each component in that system. We think that's the only way we'll get to this goal of ours, which is imagery in each eye that is compromise-free in the face of rising 2D standards. All right, so this is the talk, motivation we just talked about. We'll talk about some new 2D cinema contrast experiments that we've conducted. We'll then talk about 3D encoding methods and some of the image quality that those encoding methods contain. And then I'll just have a summary. All right, factors affecting the overall contrast in the cinema. Well, we see that in the cinema there are a lot of sources of light, essentially. There's ambient lighting, there's reflection from the screen off of the seats, reflection off the walls, reflection off the floors. You may have egress lighting that sits very close to the screen and can pollute the screen darks. Patrons themselves, as you project on a screen, light bounces off that screen, bounces off the person that's sitting next to you, goes back to the screen. That pollutes the dark state also. This is a typical premium large format theater, some imagery that we take with a colorimeter, imaging colorimeter. You can see that the light that's bouncing off a seat can be in the 0.3 to 0.7 nit range. It's a lot of light coming back from each area. So we wanted to measure this and understand what sort of levels of light are coming back onto the screen from all the other contributions in the theater. We first would put up a white screen, make a measurement, put up a dark screen, make a measurement. That would give us the projector's sequential contrast. Then we would put up a chart like this. It looks a lot like an ANSI chart. Basically, it's a full white screen with a bunch of holes in it. The fill factor is about 72%, so we get about 72% ambient light coming back off the screen. We can then scale the results to whatever average illumination we really want. Then we use an occlusion, so we actually cast a shadow in each of those areas so that we can measure the contribution of the people and the entire theater, what's going to the screen from those contributors. And we measure that with what we call a stray light illumination tube, or a SLET. That's essentially a baffled tube with a very sensitive detector at the end of it. This is a NIST standard, something that was actually developed in Boulder, Colorado, and we've used this quite a bit in our testing. So here's some of the data. You get an idea of what theaters look like. We measured 8 theaters, sequential contrast of the projectors. Normally a DLP projector in the cinema starts at about 1,500 to 2,000 to 1 sequential contrast. As it ages, though, you see a little bit lower contrast. Dust enters the system. You've also got contributions from dust on the port window. So average about 1,100 to 1. The veiling contrast, that's contributions in the projection lens itself. So scatter in the lens, AR coatings, any light that bounces off the barrel itself and gets to the screen creates a veiling glare. That's about a little over 1,000 to 1. Room contrast, all the surfaces in the room, in a typical theater room, that's about 1,500 to 1. And you can see those numbers are pretty stable. So these are widely varying theaters in terms of geometry, yet oddly enough, the contribution of all those surfaces is pretty consistent. And finally, the system contrast, that's what we measure the bright versus the dark state on the screen. And really, we're achieving about 350 to 1. Sounds kind of low when you start talking about, HDR. So we can take all those factors and we can create an equation. And that equation really determines the system contrast from the projector sequential contrast, the veiling glare, the seats in the auditorium, the surfaces in the auditorium, and then the number of people that are actually in the auditorium. We have a factor A in there. You know, if someone's sitting in the seat, well, they cover up the seat, so you take that contribution away. And if we look just at the projector sequential contrast, and then apply this formula to the for the system contrast, and then we say, okay, let's talk about an empty auditorium. We can plot some curves for different average luminances. So here we've plotted 5% average luminance, 10%, 15, 18, 20%. We chose those numbers because those are actually real numbers. You know, in the cinema, about 50% of your content is 5% or less average luminance. About 90% is somewhere below 20%. So we looked at system contrast versus projector sequential contrast, and at the bottom there you see a projector sequential contrast going from 1,000 to 1 all the way up to 1,000,000 to 1. And you can see as we plot this data, there's a knee in the curve of every one of these curves. It doesn't matter what average luminance you have. Really, it's about 10,000 to 20,000 to 1. And so for your typical theater, for your typical PLF, premium large format theater, which these are theaters that we measured, it seems that 10,000 to 20,000 to 1 is a pretty good number for your projector to have. You go above that, you get some benefit, but not a lot. It seems like we've hit a saturation point there. All right, so that's 2D system. Now let's talk a bit about 3D. 3D has its own contrast factors, and it all starts with the encoding system. So right now there are two prevalent encoding systems out there in the cinema. One's polarization encoding, one's 6 primary spectral selection, or what we call 6P. So polarization, there's a modulator at the projector. We place something in front of the projector. We control the polarization states. And that can be compatible with any number of primaries, 3, 6, 8, whatever number of primaries you want. All those primaries go through that polarization encoding system. 6P spectral selection, well, you need no modulator at the projector. Really, you're projecting different laser wavelengths. And so, but you have to split those wavelengths up into 2 eyes. 3 primaries for the left eye, 3 primaries for the right eye. Polarization systems, you have a polarization preserving screen, typically has a gain of about 2 to 3. Big advantage of 6P is that you can use a white screen, and it has a gain of about 1.8. The eyewear and polarization systems are very low cost, and they use absorption to reject unwanted light. Whereas 6P systems, they use multi-band dichroic eyewear. So these are thin films. And they use reflection to reject unwanted light. To give you an idea what that looks like, there's a picture on the left side. There's a polarization set of eyewear. On the right side, there's the 6P multi-band dichroic eyewear. All right, we're going to look at some image quality metrics. Really luminance uniformity, color uniformity, stereo contrast ratio. Those are all very typical for 3D cinema. And we're also introducing a new term today called viewer ghost contrast ratio, and I'll explain that a bit more as we go along. Screen geometry, we have to make some assumptions on screen geometry. Standard cinema is around a throw ratio of 2. And I like coming to Display Summit because people know what throw ratio is. I don't have to explain that again. But throw ratio 2 is about standard cinema, so you can see that the angles are, somewhere in the range of 20, 25, 30 degrees for the half viewing angle if you assume the viewer is sitting halfway between the projector and the screen. Long throw special events, you can have low numbers, low angles about 10 to 15 degrees. And for premium large format, these are the big theaters that are becoming very popular, and they're also producing a lot of money these days for cinemas. Those can range anywhere from throw ratio 1.5 and down, and so you can get a half viewing angle of about 30 to 45 degrees, very large angles. So we can measure the laser spectra. This is a normalized 6P spectra. We can measure eye wear, so we can put that on a rotating stage, put it in a spectrometer, rotate it about the eye's pupil. And we can see 6P blue shift. So, multi-band passed dichroic filters, they are thin film devices. And thin film devices, as you change the angle of incidence of the light coming into them, they change, they blue shift. They essentially change their transmission peaks, they move towards the blue. So at 0 degrees, we see on the left side, the left eye light goes through transmits well through the eye wear. Right side, the light goes through, the spectral peaks go through transmit very well through the right eye wear. But as we start to shift, 5 degrees, 10 degrees, 15, you can see the transmission peaks shifting. 25 degrees, we're starting to lose light on the left side, on the left eye, and we're starting to introduce the wrong light on the right side. So we're getting ghosting, essentially. Getting ghosting from the left eye image. So we continue 30 degrees, now we're getting a lot of ghosting, and we're losing light in the left eye. 40 degrees, or 35 degrees, still more, 40 degrees. We've essentially lost all of our light in the left eye, and we're seeing a lot of ghosting in the right eye. All right, we can take those measurements and we can do an analysis. So we start with the screen. We can calculate the illuminance that comes to the eye. Well, actually we have two screens now because we have a left eye and a right eye. Each of those have their separate spectrums. We pass that through the eyewear. The eyewear we've characterized in terms of wavelength and angle. We can calculate some efficiencies. So the efficiency for the pass band, the amount of light that comes through that you want in that eye. You can also calculate the stop band efficiency, the light that you don't want to come through to your eye. And we get these eta factors. We can use these factors to determine the luminance roll-off, the stereo contrast, and we can also look at the color shift in the eyewear. All right, so some results on the left side here is brightness uniformity. The bottom of the graph is this angle that we were talking about. Remember, 40 degrees is around the PLF size environment. So the right eye is the green dotted line. That's luminance uniformity. And you can see it stays pretty good, all the way out to about 30 degrees, and then it starts to fall off a bit. Whereas the left eye, as we expected, because of that blue shift, we see that the left eye does fall off rather rapidly. Starts at about 20 degrees and keeps going. The other side of the graph is color uniformity. That's delta U prime V prime. You can see the DCI limit is that purple line at the very, very bottom. The right eye does a pretty good job. The left eye starts to drift off pretty quickly. And that's essentially because of the loss in light. Stereo contrast. 6P systems have great stereo contrast on axis. 20,000 to 1, we can't even measure it, and that's because the leakage from the projector sequential state comes through eventually in the correct eye, so you can't essentially measure that. The left eye stays very, very good all the way through the angular range, but the left eye doesn't really have any light in it at that point. The right eye starts to fall off again, 20, 25, 30 degrees, starts dropping down. So, those are essentially simulations based on measurement. We wanted to measure things and compare that to a polarization system. So we used an imaging colorimeter and placed the eyewear in front of that and looked at it on a real screen with a laser projector. These are some of the images from that. You can see the left eye, just what we expected. The illumination drops off and there's a lot of color that comes into play as you get out to these PLF size screens. The polarizing eyewear on the right, both the left and the right lens look very similar. That stays pretty uniform throughout the entire image. The 6P right lens performs very similar to the polarization system. These are stereo contrast measurements. So the left eye, left lens and the right lens. On the top is the polarization system, on the bottom is the 6P system. Again, polarization system is certainly lower in stereo contrast than the 6P system on axis, but it maintains that contrast all the way to the edge. whereas the 6P system does lose stereo contrast at the edge. All right, we're introducing a new concept today called viewer ghost contrast. What viewer ghost contrast is as you look at a screen with a dark area in the center, the light from outside of that area you're looking at pollutes the scene you're looking at by creating an image in front of your eye, a ghost. So the way that happens is if you have light that comes through, that's the spectrally selective light gets the eye, you get what you want, but that same passband light hits your skin. Your skin is a Lambertian reflector. It changes angle. That angle could be reflective now, very reflective, and you can see a ghost. In the same way, off-axis light, that's light that sees a blue shifted passband filter or stopband filter, that reflects off the skin, gets back to your eye, creates a ghost image. Some of those two, the passband contribution and the stopband contribution, give you your viewer ghost. These are some images of viewer ghosts. So 6P, we took a mannequin, placed a camera behind the eyeball, and looked at the images on screen as we projected a large circle around a center patch. So you can see that the 6P eyewear, pretty strong reflection. Standard circularly polarizing lenses, it's certainly knocked down quite a bit. If we add an AR coating on the back side of that, it really knocks it down. So we did some analysis again. We used the same analysis that we did before. We pass light through the screen, through the eyewear. That light hits the skin. That light becomes, again, another illuminator. So it has a luminance, and that luminance is determined by the amount of light coming in, and also the reflectivity or albedo of the person's skin. We can then determine what the reflected image looks like based on those same sort of efficiency numbers in reflection. And then we can compare the light that's coming through that you want to come through versus the reflected image, and we can get this viewer ghost contrast. And I know that's a lot at 8:30 in the morning, so on a Monday. So there's a paper from SID if you want to take a look at the equations. So we went ahead. The rubber hits the road when you make measurements. We made some viewer ghost contrast measurements. We used a very sensitive camera, an aperture in the front, and we placed a small Lambertian target on the aperture. That represents your skin. We know it's a higher reflectivity, but we can scale the results. Then we looked at images that look a lot like this. They have a central obscuration area and then white around, a white surround. And we varied the images so that we could get some decent test data. We also measured, of course, white and dark. So simulation and results. Well, the dotted lines in the bottom, that's the 6P system, the green and the blue dotted lines. And our measurements, which are the aqua and the magenta lines, those compared very well with our simulations.
What screen is that?
The screen we used there was one of our RealD screens.
The white?
Precision white.
Precision.
Yeah. So you can see that the results matched up pretty well. We also simulated the polarization system, and that's the red line at the top. Now we expected that to be very high performing because the only reflection really is off the front surface. The back surface acts as an optical isolator. It really is a circular polarizing system, so we expected that to be better. You can see the results are a bit lower than we expected, and the reason is really scatter in the films, scatter in the adhesives that hold the films together, and so we know we have some improvement there. Okay, here's a summary. Luminance, you can see the polarization system and the 6P right system. They both have rather good uniformity. The projector roll-off is included in this. But the 6B left eye, it really drops pretty fast in luminance. Color, again, polarization and the right eye of the 6B system hang in there pretty well with the DCI limit, whereas the 6B left eye, you know, sort of juts off into space, and you know, to change the scale a bit, you can see that you know it's quite far off. But a lot of that's really because there isn't any light out there anymore, so you know, essentially measurement error. Stereo contrast, again, the polarization system, the red and aqua lines there are, it's pretty uniform in the polarization system, but certainly lower than the 6B system on axis. The 6B system stays pretty good until, you know, about 25 degrees, and then it starts dropping down quite a bit. We have a new screen technology at RealD. This is the screen you're talking about. We call it the ultimate screen. It's a roll-to-roll process. We feel we can get that number up to about 300 to 1. And finally, viewer ghost contrast, this new term that we've introduced. Again, the 6B system. It's fundamentally limited to what you see here. The RealD polarization system, you know, we feel if we can make some improvements in our process, we can get that up quite a bit. So, summary. Talked about 2D system contrast. Well, we measure that in theaters, and we can use that now to drive projector specifications. And we feel from the data that we have so far that 10,000 to 20,000 to 1 projector sequential contrast, that appears sufficient for enhancing cinema dynamic range. 3D system performance, well, it's really highly dependent on the 3D encoding scheme that you use. So dichroic 6B systems, you know, they provide high on-axis stereo contrast, but they're asymmetric from eye to eye. You know, they provide degrading performance as angle increases. Polarization systems, they provide a very symmetric performance over the entire PLF angular range. And viewer ghost contrast, this new term that we've introduced, we feel that's fundamental to 6B systems. There's not much you can do about that in the dichroic design. While polarization systems, well, we have some room to improve on our current advantage. Finally, a systems approach to 3D presentation, we feel that's the right way. That's going to provide us the best chance of meeting this no compromise 3D imagery in the face of the new 2D standards. All right, a lot of contributors, and again, thank you, Chris, and Display Summit.
Any questions? When can we get the new screen?
The plan is for next year, sometime next year, 2016.
Yeah, here you go. Thanks for that detailed analysis, but it seems like you're doing the perfect case, which we need to do. Do you have a feel for what the viewer actually sees? Like I go and I get smudges on my glasses, so I clean them with my hanky. And I can't always sit in the center where I want to sit, so I'm at the edge. What kind of tolerance is there? And the second question part of that is the viewer tolerant of what you have, or does he want something better?
Well, I'll start with the second part. I think the viewer wants something better. I think we all want something better. I put on the polarization eyewear, and I see the haze. I see the issues. I put on the 6P eyewear, and you know, I really see the asymmetry that really bothers me, and I see the viewer ghost contrast. In terms of where you sit, the geometry, polarization systems are more dependent on where you sit. But they're still a little more uniform. The 6P systems, again, if you sit, you know, off on a far right seat or a far left seat, now you're getting more angular variation in one portion of the image, so you may even have worse results. Hi, Bill.
It's not a display summit without a question. You mentioned very briefly that in your data you included the projector roll-off, and I wondered if you could comment on what your data showed and whether there's a difference between laser projector roll-off center to corner versus a typical xenon projector in the field, roll off center to corner, and how does that impact your results?
Oh, good question. Honestly, no. We didn't look at that. I apologize. I think you probably know better the difference between a xenon projector and a laser projector roll-off. I expect that the laser projector is going to be much better, be much more uniform. But honestly, we didn't have time to factor that in. These are pretty fresh results.
I imagine they are. I think qualitatively, the laser projector, at least the one I'm familiar with, is more uniform center to corner, and I think that helps in any gain screen situation, just in general.
I would agree. Yeah. Anytime you can boost that edge up, the image is going to look better. It's part of the reason we went on this quest to get a new screen material. Also, we wanted to improve the angles. In a gain screen, of course, the edges just drop off to nowhere in terms of luminance, and we really wanted to be able to control where that light was going. Just like you do in your projectors, you want to control where that light goes. We want to, once you give us that great image, we want to present it back to you.
One other just general question. In the PLF world, do you have a sense of what the average throw ratio is, or is it all over the map?
It's usually below 1.5. Yeah, it's usually below 1.5. We get a lot of requests for our XL product our initial XL product is limited at throw ratio 1.4. And we are getting a lot of requests for our next follow-on product, the XLW, which goes down to 1.0, and our GS product, which goes down to 0.8. So those products are really ramping up right now in a big way. So you can tell that these PLF theaters, these short, squatty boxes, 1.4 isn't enough. They need to go below that.
You really need a high quality zoom lens in the 1.2 to 1.4. Like Hyperion is willing to build them for like 30,000. You guys should phone me out.
Excellent idea. Excellent idea. And while I've got the PhD corner, do we have time for it? Yeah. In the first part of your talk, when you were defining contrast ratio and all the different elements with contrast ratio, with your SLET measurement device, were all those measurements on axis?
Yes. Yeah, the SLET has a very narrow angle. It's probably a field of view of around.
No, I get that, but did you take any measurements?
I'm sorry.
From the corners.
The measurements you saw, those are averages from each one of those squares. So yes, we took all the corners and the center, and we averaged all of those. And so the numbers that were in that slide, ways up there from the eight different auditoriums. Those are averages of all of those different places on the screen, all those locations.
But the SLET stayed in the center?
So the SLET, we moved the SLET. We aimed the SLET. We had a laser pointer on the SLET, and we could point it at the right spot, turn the laser off, and make a measurement.
But it was positioned in the center of the theater.
Yes, it was positioned in the center. Yeah.
Okay. Can you explain about ghost busting? How much it affects?
Explain about ghost busting.
Yeah, we played at Soho House Jurassic World yesterday, and I didn't have the ghost busting file, but it looked pretty good.
Yeah, the content providers are getting really quite good at sensing when ghosting could occur and mitigating that in the content. I think most content these days.
Have you considered creating a general ghost busting for alternative content so that we can?
Yeah, our approach is that hopefully we can cut the ghosts down so that ghost busting is just unnecessary.
But if you play a Blu-ray on a PLF, whatever you call these, I do PLFs for homes with very expensive kit, and I get a lot of, I get like 15% ghosting. It's the best picture.
Oh, I can talk to you more about that.
Yeah, let's thank Miller. Thank you.
Are you sitting here? Yeah. Oh, yeah. I worked with, he no longer works there, but we did a few Soho houses. So I'm doing now 3 more Soho houses. And I also did the first real projection.